Hi, in this video, we're going to talk about how to implement quicksort. Now, implementing quicksort was a pretty interesting coding experience for me when I went through it. So for those of you who like to get good at technical interviews and you have time to practice writing code, then I encourage you to try to implement quicksort on your own first. Now, there are at least two general approaches to implementing quicksort. Well, both of them will meet the requirement of doing it in place. However, the first approach, you can use extra lists and use list slicing to kind of help you along the way. And if you do this, it's much easier, I think. Now, if you want to sort the input completely in place without using any extra list, then I think this approach would be quite a bit harder. But either way, there are tests that are already written for you. So at least in that regard, it kind of, in a technical interview, you don't get tests written for you. You have to test your own code. But in any case, we already have tests. So if you do want to implement quicksort, make sure to take advantage of tests that, can verify your implementation is correct. And next, I'm going to show you the easier version first. Okay, so this is the quicksort implementation that uses extra list, and I call it quicksort_el extra list. Anyway, so remember it is a recursive algorithms, and the base case, as you can imagine, is either is an empty or a list with a single element. In that case, we don't need to do anything, it's already sorted. Otherwise, we'll create a list to hold all the elements that are smaller than the pivot, and another empty list that holds all the elements that are bigger than the pivot. And then, as we said, we pick a pivot, and in this case, let's stick with the basic and just pick the first element as the pivot. And then we basically just go through the rest of the elements in the input, and if it's smaller than the pivot or if it's equal to the pivot, in this case, we'll just put the element into the smaller list. Otherwise, if it's bigger than the pivot, then we put it in the bigger list. And then we recursively sort the smaller list and the bigger list. And then when we're done, we'll concatenate the smaller list, which is now sorted, with the pivot. The pivot should be between the smaller partition and the larger partition. And then finally concatenate the larger list together, and we'll update the entire iterable with the result. And that's it. It's pretty straightforward. And know that, yes, so this approach is in the alternative. This implements the alternative approach that we kind of discussed earlier, that we're putting the pivot in between the small and the large partition at the last step. Okay, and I hope this makes sense. And then, as usual, when we write a test, we should test it, and this is how we test it. Again, you know this already, so I'm not going to go over it again. Next, I'm going to talk about how to implement quicksort completely in place. So if you still want a bit of time to at least think about how to do that on your own, now is the time to pause the video and think about it. And here it goes. So if we cannot use any extra list to hold any of the intermediate results. So this is, by the way, this is how the original quicksort was written back in the late 50s and early 60s. Anyway, so in order to do that, we kind of have to figure out how the partitioning, how that process works, and where to hold all the intermediate results, right? So the basic idea is that we'll maintain two pointers, a obviously, in addition to the pivot. So we maintain a left and a right pointer. Okay. Now, the significance of these pointers are, for the left pointer, all the elements, when we are done, all the elements to the left of the left pointer should be elements that are smaller or equal to the pivot. Okay, so, and note that when we start, there's nothing to the left of the left pointer, right, other than the pivot itself. So, which kind of makes sense, because again, when we first start, we don't know if there's any element that is smaller than the pivot. So there's nothing in the smaller partition right now. And then the significance of the right pointer is that all the elements to the right of the right pointer, they should be larger or equal to the pivot. Okay. And again, notice when we first started, there's nothing to the right of the right pointer, which totally makes sense because we don't know if anything is larger than the pivot just yet. And our goal for the left and the right pointer is that we'll move the left pointer to the right and the right pointer to the left, such that we'll put all the elements in the right place. And then at the end, when the right pointer gets to the one position left of the left pointer, then we would know that we are done partitioning all of the elements. Because if you look at where the right pointer is, everything to the right of the right pointer, which is this part, the green part, these are all the elements that are bigger than the pivot. And then everything to the left of the left pointer, which is this part, the slightly yellowish part, these elements are all smaller than the pivot. So that's the condition under which we know we're done moving the left and the right pointers. And this terminating condition is kind of super important to the partitioning process. So keep that in mind. All right, so now let's look at how the partitioning process actually works. So when we first start, left is pointing to 7, right is pointing to 1. Now the left 7, the number 1 that left is pointing to is 7. It is bigger than 4. So we know this is in the wrong place, right? Because on this side, it should be something that is smaller. Now 7 is bigger, so we have to move it. Now where do we move it to? Well, look at the right pointer. The right pointer right now is pointing to the number 1. Number 1 is smaller than the pivot, so we know 1 is also in the wrong place and in the wrong part of the list, right? So this is great. We have something that's too big that should be in the bigger partition, and we have something that should be in the smaller partition. And all we have to do is we just swap them, right? And then they will be in the right place in the list, and then we can move the left pointer to the right and the right pointer to the left. So this is the next picture. We swap 1 and 7, and then we move both pointers. Now we look at the next number, 9. What 9 is pointing to? Well, 9 is bigger than 4, bigger than the pivot. So again, it's in the wrong place. But let's look at what right is pointing to. Right is pointing to 8. 8 is bigger than the pivot. So it's in the right part of the list. Right? This part is any number that is bigger than the pivot, and 8 is in the right place. So it doesn't make any sense to swap 9 and 8. Right? We really don't help the situation by swapping that. So what we need to do is we gotta now keep moving the right pointer until we find an element that is out of place so that we can swap it with 9. So we move it down to 5. 5 is still bigger than 4, and so 5 is also in the right place. So we keep moving until we get to 3. 3 is smaller than the pivot and it's in the wrong place, and it's then we can swap 9 and 3, both of them out of place, so that they are now in the right place. Now after we swap them, we moved left and right pointer again, and now they are pointing to the same element. Okay, now we go through the same process. We look at the left pointer, and left pointer is pointing to 2. 2 is smaller than the pivot, so it is in the right place. Therefore, we just move the left pointer one more to the right, and then check 9. Now 9 is something that we already look at. Well, actually, we don't even need to check 9. Before we check 9, we should check, okay, between the 2 pointers, the right and left, are we done? And we've reached the condition under which we are done, because now the right pointer is 1 position to the left of the left pointer. And if you remember what we said earlier, that kind of signifies we're done with partitioning. And if you look at this thing, and yes, we are done with partitioning. So yeah, we're finished with partitioning in this particular pass of the quicksort. Okay, while we are done with the partitioning itself, we're not completely done in terms of the algorithm, right? Because this pivot is still out of place with regard to the smaller and the larger partition. So if you remember from the algorithm, what we should do is that we'll swap 4 with the last element in the smaller partition. Okay, so we swap 4 with 2 in this case. And what that does is it put the pivot in the right place between the smaller partition and the larger partition. And then now we can recursively call quicksort on the smaller partition and quicksort on the larger partition. All right, now that you know how this thing works with the small example that we had, then you can look at our favorite visualization tool that it actually show you a larger example of how the quicksort would work. So I'm just very quickly going to go over this. So when I click quicksort, the first thing it does, it picks the first element as the pivot, and then it actually maintains the left pointer. They call it the I, and then let me move this, and then they maintain a right pointer, which they call the J, and it basically, the next step is going to do is, okay, is I out of place? Well, it is. So and then it looks at if J out of place. Well, it is in the right place, so we cannot swap I and J, but it will keep looking for, you move J to the next one, and J is smaller than the pivot, so it is out of place, and it will swap the element at I and J. All right, so you see they're just swapped, and then it basically just keep moving on. Now it looks at the current I don't know if that's bigger or smaller. I guess that's bigger, and then this one J is also bigger, and it keeps moving. And then J, now the new J is smaller, so it will swap the 2. Okay, so it keeps on going like that. So yeah, hopefully that makes sense now. All right, now that we know how quicksort works in general and how the partitioning works in detail, we are ready to look at the code, which I already typed up. As a matter of fact, I actually went through several versions of the quicksort implementation that I actually left in the source file that you can look. But this final version is the one that I'm going to explain. And so the way it works is, well, quicksort as before, because there's a recursive call, and because we're going to sort smaller and smaller version part of the input, so we have to have a start and an end index. However, we don't want the client to always have to specify the start and end. So if by default, if it's none, then we know we're sorting the entire input. And also, as usual, the end index, I like to use exclusive. And that is why the end index is the length of the entire iterable. And then, yeah, we use a nested helper function, partition, that split the input into the smaller and the larger version. And it actually returns the index at which point that it splits. So, and that's where the pivot currently is. So basically, yeah, the right pointer when we are done here. Okay. And then let's see, I mean, this line should be very familiar. If if the list only has a single element or 0 or empty, then we're done. And the rest of the code just works as expected. We partition the input, and then we get the return as a return value from a partition where the pivot is. Then we'll quick sort everything that's from start up to the pivot, but not including the pivot. Right? Remember, this is exclusive. And then we quick sort the larger part, which is the pivot plus 1 all the way to the end. So that's a recursive two quick sort calls. Okay, so let's look into the details of the partition function, which is probably the most complicated part. So the first thing we do is we pick out the pivot, which is the first element in the input, and then we initialize the left pointer, which is one position to the right of the pivot, and the right pointer, which is the pointing to the last element of the input, and then we loop through this. And just remember, the goal is, at least for the left pointer, is that we'll keep moving it as long as it has not raged past the right pointer, and also as long as the element at the input, well, the element of the input at the left pointer is in the right place, right? As long as it's less than or equal to the pivot. So we keep moving it until we hit either of these two conditions. And then the same for the right pointer, as long as it hasn't passed to the right of the left pointer, and as long as the element at the right pointer is in the right place, then we move the right pointer, but we move it backward. That's why it's a -1. And then here is the condition. Remember, our terminating condition is when the right pointer goes to the left of the left pointer. And if that were the case, we know we are done. Otherwise, we know the left and the right pointer, they are pointing to two elements that are both out of place. In that case, we can just swap them, right? And when we're done with this loop, that means everything's in the right place. That means we are in this picture now. And then the next picture we're going to do is just we're going to swap what's at the pivot with what's at the right pointer. So that's what that when the loop is done, that's what this thing is doing. And then finally, remember we said we want to return the place where the smaller partition and the larger partition is split, and that's where right is pointing to and where the pivot is currently. So that's why we return right pointer. And as usual, now that we have an implementation, we should test it. And here's the test code, can run it, and we pass all the tests. And usually the next thing that we do is we will talk about performance, but I'll do that in a separate video. However, I just want to do a quick comparison between our two quick sort implementation. The first one is using the helper list. And then the second one is our strictly in place quick sort. And to my big surprise, that the quick sort that used all the extra helper list it's actually faster than the in-place quicksort. And so this really kind of had me scratching my head, because I know the Python's list manipulation is supposed to be fast, but then creating extra lists and all that, it should still take more time. So at the moment, I'm not entirely sure why using extra lists would be faster than the strictly in place implementation. So I would ask you to kindly repeat the test runs, and then maybe share your results in the forums, and then let's discuss it.